Alright guys, I'm going to talk to y'all about linked genes and map units and sex-linked genes today. So the first section I'm going to talk about are linked genes. So linked genes is referring to genes that are physically close to each other. So these are genes that are located on the same chromosome. And the closer they are together, the less likely they are to be recombined during crossing over based on their location. So if they're physically close together, they're usually inherited together. So an example, and something that you guys probably see and know about is freckles and red hair. It's not very often that you see someone with red hair and no freckles. Usually if you have red hair, then you also have freckles because those genes are really close to each other. So if my gene for red hair is right here, the one for freckles might be right here. So since these are really close together, whenever the homologous chromosomes are crossing over, they're likely to switch the bits of information that are right next to each other. It's more likely that they're going to swap together than for it to break right in between those because they're so close to each other. So the closer they are, the lower that recombination frequency is because the odds of it breaking in between there are lower. Now, if they're farther apart, so let's say we're talking about the red gene and this green gene up here, okay, those are really far apart. So the odds of them being separated when they're crossed over are a lot higher. So they have a higher recombination frequency. Now about sex-linked genes. So sex-linked genes, I'm going to zoom in because there's a lot more writing that I have to do. These are genes that are coded for on the sex chromosome. So in humans, that would be the 23rd chromosome. Okay, as a friendly reminder, in females we have XX and males have one X and one Y. So a lot of these that we're talking about are located on that X chromosome. So depending on if the trait we're talking about is dominant or recessive, you might see some different things in the pedigrees. So I'll start with the dominant one. So if you have a dominant allele, then it's going to express that trait. So in this pedigree that I have here, I have a male who is XY. Okay, he expresses that trait, and if it's dominant, much like a regular Mendelian stuff, we would use a capital allele. So I'll just use a capital A. So this father expresses a trait because he has a dominant allele on his X chromosome. Now the female, on the other hand, she's XX, but she does not express the trait. So in order to not express the trait, she can't have a capital A for her allele. She has to have two lowercase alleles. Okay, now if I'm looking at my offspring here, I have two females, a male, and here's my other female. So my females do express the trait. Okay, the reason we can tell this is because it's shaded in, so they have to have at least one capital A. That one capital A they got from their father here. Now I'm losing my train of thought, sorry. So the second one, the second X they get from their mom, which is going to be a recessive one. That would make them carriers. A carrier is somebody that carries the recessive allele but does not express it. So they don't express the trait. Okay, so these two females are going to be carriers. Now my male is an X and a Y, so he gets one Y from the dad, and his X is always going to come from the mom, which is a little a. So in the case of a dominant sex-linked trait, if the father has the trait, he's always going to pass it on to his daughters because the daughters get one X from dad, and he only has one to give. So if his is dominant, every single one of those daughters is going to get his dominant allele on his X chromosome. Okay, in this case, the males are different because they only get it from the mom. So the mom would have to be carrying it, or she would have to express it if she was going to give it to her son if it was a dominant trait. Now, if it's a recessive trait, these are the ones that we're used to talking about. So the example we typically use is hemophilia. So let's say I'm going to talk about like the Romanov family. So if you've ever seen the movie Anastasia, it's based loosely, very loosely, on a true story of the Romanov family, who were royalty in Russia. So there was a queen and a king. Neither of them had hemophilia. So my dad has normal bleeding, which I'm going to use with a capital H, and the mom does not have hemophilia. So we know that at least one of hers has to be a capital H. The other one we're not sure about because we don't know yet. So the Romanovs had a bunch of kids. Unfortunately, to their throne, they were all females. So the females get one X from mom, one X from dad. So one X we know has to come from dad, so it's a capital H. Not going to have hemophilia. Second daughter gets one capital H from the dad. We know it has to be capital H. Second one, we don't know from mom. Third daughter gets a capital H on her X from dad, and the second X from mom. Fourth daughter, first X is dominant from the dad. Second X, we don't know from the mom. Now the son, all of a sudden, they've been going and getting girls all this time, so Russia thinks they're cursed. And then they finally have a son, and lo and behold, he has this life-threatening disease called hemophilia, which is a recessive sex-linked trait. So if he's expressing it, that means he has to have the lowercase recessive hemophilia gene on that X chromosome and the Y from the dad. So that means that my mom, or the queen, has to have a lowercase h on hers. So if you're looking at recessive sex-linked traits, the males are always going to get it from the mom, because the mom is the one that gives the X, the dad is the one that gives the Y.